Black holes, as described by general relativity, are regions of space-time where gravity is so intense that nothing, not even light, can escape once it crosses the event horizon, the point of no return defined by the Schwarzschild radius for non-rotating black holes or the Kerr metric for spinning ones. Formed from the collapse of massive stars or through mergers as evidenced by the 2025 detection of the most massive black hole collision by LIGO Virgo, these cosmic entities warp space-time dramatically, creating an inescapable gravitational well. From an external observer's perspective, matter falling toward a black hole appears to slow down asymptotically due to gravitational time dilation, never quite reaching the horizon, but, in reality, the infalling material crosses it in finite proper time. Inside, the laws of physics as we know them begin to falter, with tidal forces stretching objects in a process called spaghettification, where the gravitational gradient pulls harder on closer parts, elongating and disintegrating anything that enters. This interior realm remains shrouded in mystery, as no information escapes, but theoretical models suggest a journey toward a central singularity where density becomes infinite and space-time curvature diverges. Recent observations like those from NASA's IXPE mission in 2025, measuring polarized X-rays from accretion disks, reveal how matter behaves just outside, hinting at the chaotic dynamics feeding into the black hole's maw. Ultimately, understanding the interior requires reconciling general relativity with quantum mechanics, a challenge that has spurred theories from string theory to loop quantum gravity, each offering glimpses into what might replace the classical singularity. As an object approaches the event horizon, space-time distortion intensifies, with light paths bending severely and clocks ticking slower relative to distant observers, a phenomenon rooted in Einstein's equivalence principle, equating gravity to acceleration. For a supermassive black hole like the one in M87 imaged by the Event Horizon Telescope, the horizon spans millions of kilometers, allowing for gentler tidal forces compared to stellar mass black holes, where spaghettification occurs far outside. Once past the horizon, the radial direction becomes time-like, meaning escape is as impossible as traveling backward in time, and all paths lead inexorably to the singularity. Inside, the metric inverts. Space and time swap roles in the Schwarzschild coordinates, turning the horizon into a one-way membrane. Matter compressing under its own gravity heats up tremendously, but without escape routes, this energy contributes to the black hole's mass, adhering to the no-hair theorem, which states that black holes are fully characterized by just mass, charge, and angular momentum, erasing all other information about the infallen material. Quantum effects near the horizon, however, complicate this picture, as virtual particle pairs from the vacuum can become real, with one falling in and the other escaping as Hawking radiation, slowly evaporating the black hole over eons. Crossing the event horizon marks a profound shift, where an infaller experiences no immediate drama due to the equivalence principle. Locally, it's like free fall, but globally, they've entered a causal disconnect from the outside universe. For rotating black holes described by the Kerr metric, an inner ergosphere allows energy extraction via the Penrose process, where particles can gain rotational energy before escaping, but inside the horizon, even this ceases. The path inward leads to the Cauchy horizon, a secondary boundary plagued by instabilities from blue-shifted radiation, potentially forming a firewall of high-energy particles that incinerates anything crossing it, as proposed in resolutions to the information paradox. This firewall hypothesis, debated since 2012, suggests that quantum entanglement breaks at the horizon to preserve unitarity, challenging the smooth crossing predicted by relativity. Recent 2025 studies on black hole interiors, including those exploring white hole transitions, propose that instead of a destructive firewall, the interior might evolve into an expelling phase, ejecting matter after a finite time. Such ideas stem from loop quantum gravity, where space-time quantization prevents singularities, replacing them with a bounce that could connect black holes to white holes. Toward the singularity, gravitational forces overwhelm all others, compressing matter to Planck densities where quantum gravity effects dominate, rendering classical descriptions obsolete. In general relativity, the singularity is a point, for non-rotating, or ring, for rotating, of infinite curvature, but physicists suspect this signals the theory's breakdown rather than physical reality. String theory posits that strings smear the singularity into a fuzzball of vibrating modes, preserving information on a holographic surface rather than losing it to oblivion. Alternatively, Asymptotic safety approaches suggest gravity becomes finite at high energies, avoiding infinities altogether. For an infaller, time dilation means the journey to the singularity is brief in proper time, seconds for stellar black holes, but the extreme tides would disintegrate atoms long before arrival. Observations of merging black holes in 2025, like the record 2.5 billion solar mass event, provide indirect clues, as the resulting spin and mass align with no-hair predictions, but interiors remain unprobed. This inaccessibility fuels speculation, including 2025 theories that our universe might reside inside a larger black hole, with its expansion mirroring interior dynamics. The singularity itself represents physics' frontier, where volume shrinks to zero and density soars infinitely, defying conservation laws and causality. Quantum mechanics implies fluctuations prevent true infinities, perhaps via a minimal length scale from Planck units leading to models like the Planck star, where quantum repulsion halts collapse and triggers a rebound. In such scenarios, information isn't destroyed but encoded in outgoing radiation or emergent structures. Hawking's 1974 calculation of black hole entropy, proportional to horizon area, supports this, implying microscopic degrees of freedom akin to a thermodynamic system. The ADS-CFT correspondence in string theory further suggests the interior is holographically dual to boundary quantum fields, resolving paradoxes by storing data on the surface. For charged black holes, the Reisner-Nordström metric introduces a time-like singularity, but quantum effects might stabilize it into a traversable wormhole, though instabilities persist. Hawking radiation, arising from quantum field theory in curved spacetime, implies black holes aren't eternal but evaporate over timescales longer than the universe's age for stellar masses, emitting thermal particles that carry away mass. From inside, this process is invisible, but it poses the information paradox. If radiation is purely thermal, information about infallen matter is lost, violating quantum unitarity. Resolutions include subtle correlations in radiation, via soft hair, or the firewall, where the horizon becomes a high-energy barrier to preserve entanglement. 2025 research on black hole thermodynamics, including white hole transitions, suggests evaporation culminates in a burst, releasing trapped information. For primordial black holes potentially formed in the early universe, evaporation could be observable today, offering tests of these ideas. The information paradox, central to black hole interiors, questions whether quantum information is conserved or destroyed at the singularity. Hawking argued for loss, but modern consensus favors preservation, perhaps through holographic encoding, where the 3D interior projects onto the 2D horizon. In 2025, simulations using quantum computers model toy black holes, showing information scrambling but eventual recovery in radiation. This aligns with the ER=EPR conjecture, linking wormholes, Einstein-Rosen bridges, to entanglement, suggesting interiors connect distant points via quantum tunnels. Quantum gravity theories like loop quantum gravity quantize space-time into discrete loops, replacing the singularity with a finite bounce, where collapse reverses into expansion, potentially birthing a new universe. String theory's fuzzballs distribute mass across multi-dimensional strings, avoiding point singularities. These frameworks predict observable signatures like modified gravitational waves from mergers, as seen in 2025's massive detections. Emergent gravity ideas treating space-time as condensed quantum bits further blur the interior's nature. Recent hypotheses, including the 2025 proposal that black holes transition to white holes, suggest interiors are temporary prisons, with matter eventually expelled as the black hole flips due to quantum tunneling. This resolves paradoxes by making evaporation a phase change. Observations of waking supermassive black holes in 2025 support dynamic interiors. The universe inside black hole idea posits our cosmos as an interior, with dark energy mirroring expansion. In summary, while classical physics predicts a destructive plunge to a singularity, quantum effects paint a richer information-preserving picture, with ongoing 2025 research, from mergers to theoretical models, edging us closer to unveiling black hole interior secrets, potentially revolutionizing our cosmic worldview.